Now let's talk a little bit more about correlation.
Let's go.
Yes, so we know that the correlation coefficient, or R, is between -1 and +1. One thing I don't think I've said yet is that the correlation coefficient is nice because it actually has no units. And this should make sense because it's calculated from z-scores, or standard units. So it's not actually affected by change of scale, which really comes in handy when we want to change the scale of our data. So a few things just to cover is that adding a constant to all x or y values does not change R. So this is really nice. If we're looking at weight and height, and let's just say our height is in inches and we want to convert to centimeters, that's not going to change our correlation coefficient, which again makes things very easy. On that same note, multiplying all x or y values by a positive constant doesn't change R. And if we multiply or divide by a negative constant, all that does is changes the sign. Also, interchanging all x and y values does not change R, so this makes sense because basically the correlation between weight and height is the same as the correlation between height and weight. It doesn't matter which one comes first or which one's on the x-axis or the y-axis. And then lastly, we already mentioned this, but changing units does not change R. So again, a super nice feature of the correlation coefficient having no units. One key thing that I have to mention, even though we've already mentioned this many times throughout this series, is that correlation is not causation. Correlation does not imply causation.
Correlation does not imply causation. Why is that?
Yeah, so just because two variables are correlated doesn't necessarily mean that we can, with confidence, say that X causes Y. Instead, we see this relationship, but we don't know if it's causal or not.
So this goes back to designing a good experiment to make sure that we can see when correlation actually happens, that there is actually a cause.
Exactly. And now we know how to measure correlation. Even a perfect correlation doesn't imply causation. So an example that we have here, it says the correlation between weight and math ability of children in a school district may be positive. So the math ability may increase as the kids get heavier because they're getting older. But that does not mean that doing math makes children heavier or that putting on weight improves children's math skills.
So would you say there's a confounder there?
Exactly. I would say here the age would be the confounder. Age is a confounding variable because older children are both going to be heavier just because they're older and better at math than younger children on average. So outliers can have a strong effect on the correlation coefficient R. And even though in general we said that older children are both going to be heavier and better at math than younger children, there could be some outliers. And this is the case in any data set. We know that outliers should only be excluded for good reasons. Outliers can be anything like typos, they can be lies, and sometimes they're even real data. Data sets can have real outliers. But the problem is, if we're looking at the correlation coefficient, outliers should definitely be examined, and the correlation coefficient R should be used with caution. So this puzzle shows two examples where the correlation coefficient can be drastically affected by just one outlier. So the puzzle says for which plot does the outlier raise the correlation coefficient and for which plot does the outlier lower it? So just looking at plot A, we have this nice group of points that looks like it would form a really nice line with a positive slope. And then we have this outlier over here, this point that lies outside the rest of the data that actually would be dragging the correlation coefficient down because the correlation coefficient looks at the strength of the linear relationship, taking into account every single point. So I could draw my line of best fit like this without the outlier, but if I included the outlier, I would have to kind of make the correlation less strong. In plot B, we see the opposite. We see this group of points right here that basically has no correlation. And then we have our outlier way up here at the top. If I include the outlier, it's going to make it look like there's a nice positive correlation. But if I don't include the outlier, if I covered it up, there's basically no correlation between those points. So it's always good. This kind of shows us the importance of doing exploratory data analysis at the beginning of any study, and not only calculating the correlation coefficient as a statistic, but also looking at the visualizations, looking at the scatter plot to make sure you don't have any outliers that are really skewing your correlation coefficient. So I hope this helps you nerd out with correlation and begin analyzing data and kind of looking at the relationship between more than one variable.